Hello everyone and welcome back to another Leetcode question. So today we'll be doing a Leetcode easy question, which is to determine if given a tree, we have to tell if that tree is a subtree of another tree. So let's just take a look at the examples right here. So for example 1, we can see that for this root tree right here, this tree, the subroot is a tree with a root 4 and 2 children, 1 and 2 respectively. And we can see that this tree is evident right here, and that's why the output return is true. Then looking at example 2, although we see that the subroot is indeed present in this case right here, it is not actually a subtree because of the existence of further children. So as such, the output in this case will be false. Also, we need to take a look at another case. So let's refer to this example right here, example 3, which is that it's not enough for us to... So let us take a look at example 3, whereby if I given a tree with a root node of 1 and a children of 1, it is indeed true that the subtree with a node of 1 is present inside, because it can be found here. So these are just roughly the cases that we have to take a look at when we answer this question. Okay, what I will do is to simply give you the idea that I came with in the first place, but actually it's the wrong solution to it. But it was my first intuition when I saw this question. Okay, so what I will do is that what I'll compare is the root nodes respectively, or the root and the subroot, and I will check if the values are equal. Then what it will mean that this tree right here is actually not the same as the subroot tree, because the values here are different in the first place. Okay, so what I will do is that I'll further recurse down the left and the right, but then I'll actually use the OR operator. So for example, let's say I have a function that does checking of the root values of the tree and subtree. Then if I meet a value that is not equal, I will just return the same function, but this time I will check the left children, the left subtree with the subroot, or the function there will be recurse on the right subtree this time with the subroot. Because if this is not my root here is not the if my subtree does not contain this root, then it will either be right here or it will be right here. So that is why I use the OR operator, so that I can continue to recurse down. And then if I meet a value that is equal, then what I will do instead is use the AND operator, because I have to ensure that the left and right subtrees are the same. So for example, when I recurse to this 4 right here, then I see that, it has... Let me just use a different color. So for example, when I recurse to this 4 right here, I see that it has the same value as this. So that will mean that I have to ensure that the further subtrees are the same as well. And thus I use the AND operator, because the left and right subtrees must be the same. It cannot be an OR checking. However, this is actually the wrong solution, because firstly, what it does is that it doesn't account for the fact of example 3, which is especially why I chose to write it. Because at first when I check for the root at 1, then I will see that this subtree right here is not the same as this subtree, and my output will actually return me false. But then it should further continue to check its children, whereby it will have checked node at 1, and see that this is actually the same as this, and then return me true. So this is why this algorithm will not work. So for the correct solution, or this solution that I thought of, is to actually check whether my current tree is the subtree at every point. So at every node, I have to compare whether the tree is actually the subroot tree right here. So that will mean that what I have to do is to create a helper function to check if P and Q are the same tree. So this is actually another Leetcode question that is called same tree, which I advise you to do it first before handling this question, because I'll somewhat be going through the solution to create this same tree function right here. But if you haven't attempted it before, then it's good to attempt the same tree first. Okay, if not, let's just look at the function first for same tree. Let's just refer to example 2 in our case, and I'll just take a look at the one circle in purple. So how to actually check if two trees are the same? So you're taking P and Q, which are two trees, right? So trivially speaking, if both are null, then I'll simply return true, right? However, if either my P is null or my Q is null, means they are no longer the same. Because if hypothetically speaking, when both are null, this will have returned true in the first place. So when either one of them are null, then that will mean that they will no longer be the same. So in this case, I'll actually have to return false. Sorry, this should be an else if. Else, if both of them are not null, right, that means that they actually hold the values, right? I have to check the values equality. So I have to check if these values are equal right here. And if the values are equal, right, then what I need to do is I can further recurse down to the left and right subtree to check if the left and right of this tree is the same as the left and right of this tree. So I'll recurse to the left and right. Okay, so that'll be how the algorithm will work. So what this does is that I will just be running this algorithm at every node of the tree. Let me just continue and write a small part here, maybe. So what this does is that first at the root, right, I'll check if it's the same tree. Okay, and if it's not the same tree, right, there could be a possibility that it either lies on the left and right. So this is where we need to use the OR operator again, so that we can recurse down to check if they are the same tree for the further subtrees. So I need to check the same tree at left and the right. And if either of them contains the same tree, then I have to return true, right? So what it does is that I have to check the tree at the left or check tree at right. Because in either case, if they return me a truly Boolean value, then that will mean that indeed contains a subtree. So this will be how the general algorithm will flow. And if you're not sure, let's jump over to the coding part right now so that I can explain more in more detail.
Okay, so let's just go through the solution right now. So as per what I mentioned before, let's just write some pseudocode first. So I need a helper function to check if my tree, if two trees are equal. Okay, so I need a helper function first. So let's just define the helper function first. So define, maybe I just call it same tree, and taking in P and Q. Okay, so like what I mentioned just now, if both are none, I return true. But if only one of them is none, I return false. Finally, if both are not none, what I need to do is check their values as well as their left and right subtrees to see if they are the same. Okay, so this will be how the algorithm will flow. So let's just write it out now. So if P equals none and Q equals none, they are return true. However, if P equals none or Q equals none, so this means that only one of them will be none in this case. Because if both are none, this will have executed already. Then in this case, I'll return false. Else I will check, which is returning whether P value is equal to Q value. And also, I go down the left subtree, and same tree, P dot left, Q dot left. And I also go down the right subtree to see if it's the same. So I just recurse on both of them. So at the end of this run function, it will just tell me whether the trees are the same or not. Okay, so now let's go on to the actual algorithm. So let's just handle some base cases first. Base cases. So if both are none, I will just return true, right? Because it's kind of a trivial example. However, if my subroot is none and root is not none, then I also return true as well, right? Because something that is empty will always be a subset of the actual thing. Okay, I don't know whether I phrased this correctly, but you kind of get the idea. But if my root is none, then there will be a false, because my subroot will be bigger in a sense. Else, if all these passes, then I have to check whether they are the same tree. Check for same tree at the current node. So like example 3 and 4 right here. And if I meet something that is, and if not the same tree, then I recurse down the left and right using the OR operator. Okay, so this will be how the general algorithm will run. So let us handle some base cases first. So if my root is none and subroot is none, I'll return true. Well, if my subroot is none and my root is not none, then I'll return true as well. Else if my root is none, then I'll return false. Else what I have to do is to check whether the trees are the same. So if they are the same tree, at the root and the subroot, because I'm looking at this point in time, so they are the same tree, all I need to do is just return true. Okay, else what I have to do, okay, we don't need the else block actually, you can just treat it as an else in the next case. We need to recurse down the left and the right with the OR operator. So I return self dot is subtree on the right with still the same subroot, because we are checking if we are actually checking if the subtrees are actually equal to the subroot. Or self dot is subtree root dot left and the subroot. I guess for clarity purposes, I'll just write this as the left one first, since you will read more easily. So yeah, I guess it's a solution and I believe it should work. As for the time space complexity of this algorithm, to be frank, I'm not that sure, but I believe that the time complexity should be, based on what I think, it should be of O of n times n, where m is the subroot and m is the subroot tree and n is the root tree respectively. Because the worst case is that I have to check at every point in time. So that's why I believe this is the time complexity. And for the space complexity, I'm not too sure as well, but I believe that it should be of log n. Because at each point in time, I have to check whether at each point in time the recursive stack will have to build in log n times, because I'm going down level by level. But to be frank, I'm not really too sure about the space complexity, but I believe the time complexity is actually correct. So yeah, I'm not too sure about this. Okay, so if not, I guess that's about it. So as you can see, the solution does work, but it's probably not very efficient. And I'm not too sure if there are any more efficient methods than this, but this was a solution that I could explain in a sense. So that's why I chose this as a solution. So yeah, if you have any questions, then feel free to leave them in the comments down below. See you next time.